Hello, y'all. Welcome to lesson 87 of my DB chemistry curriculum. Today, we're talking about reactivity 2.2.12 and 2.2.13. These are HL concepts. In 12, we're going to be talking about how the Arrhenius equation uses temperature dependence of the rate constant to determine the activation energy. We'll describe the qualitative relationship between temperature and the rate constant. Furthermore, we'll analyze graphical representations of the Arrhenius equation, including its linear form. In 13, we're going to talk about the Arrhenius factor A and take into account the frequency of collisions with proper orientations. From that, we'll determine the activation energy and Arrhenius factor from experimental data. So we'll talk about how that is done. So we're going to kind of start out a little bit what we were talking about in the previous lessons. We're going to talk about how rate is dependent on two things. Now, we learned this from rate laws, and the two things it's dependent on is number one, the rate constant, and that's K. And number two, we're talking about the concentration of reactants. Because we know our rate equation or rate law is rate equals K times concentration of reactants raised to a power either 0, 1, or 2. So we know all about the reactants, but what do we actually know about K? So what is K? How do we figure it out? What can we figure out about it? Well, we know it's proportional to rate, proportional to rate. From our given equation, rate is equal to K times some concentration raised to some power. So we know those two things are proportional. And because we know they're proportional, we can generally say that a higher K is equal to a higher rate. So these are assumptions we can make based on what we already know. So the higher the K is, the faster our overall rate for our equation will be. But we also mentioned in previous units that K is dependent on temperature. So let's explore the temperature dependence of K. Temp dependence of K. We can talk about this in two different ways. Now, we generally know that a higher temperature is going to relate to a faster rate, which if higher temperature is faster rate and faster rate is higher K, then a higher temperature must mean a higher K. But we know that temperature does not change concentration of reactants. So we know again that temperature must affect K. Basically, what I'm saying is if temperature doesn't affect this part of our rate equation, it must affect that part of our rate equation. So this happens in two ways. The first, we can talk about Maxwell-Boltzmann. So in our Maxwell-Boltzmann distribution, we know that as temperature increases, therefore, more particles have energy greater than or equal to our activation energy. So that's one part of our puzzle, or how temperature affects K. We also know that if we use a catalyst increases rate, therefore it must change K. But we also know catalyst increases rate, but it does not change reactants. So because catalysts don't change reactants, it must affect K. And we know it does that by reducing our activation energy. If we combine both of these thoughts, that a temperature increase increases the overall energy, increasing the chance we will have more energy than the activation energy, and a catalyst also increases rate by reducing activation energy, then what we actually have figured out is that K is dependent on activation energy as well as temperature. So it's not just temperature. We know it must also be activation energy. Our catalyst confirms that because catalyst is not changing based on the temperature. So what we do is we actually consolidate all these, and we didn't. A man named Arrhenius did. So by consolidating observations, we get the Arrhenius equation. And that Arrhenius equation is K, the rate constant, is equal to A, the Arrhenius factor, times E raised to the power of the negative activation energy divided by RT, being the gas constant and temperature. So let's go ahead and describe each of these. We know this is our rate constant. We know the rate constant's units depend on the order of reaction. This is our Arrhenius factor, and we'll discuss that a little bit more in a bit. And our Arrhenius factor's units will actually mirror the units of the rate constant. E is simply Euler's number. This is a constant. EA is our activation energy. And the units for that are joules mole inverse. Not kilojoules, just joules. R is our gas constant. We know those units are joules mole inverse, Kelvin inverse. So that is K per Kelvin, not K for the gas constant. And lastly, we have temperature, which must, of course, be in Kelvin. So this is our Arrhenius equation. Now, let's talk about that weird unit we have here, the Arrhenius factor. So what the heck is the Arrhenius factor? It's also known as the pre-exponential factor. So this part of the Arrhenius equation is what we're going to use to take into account frequency of collisions. So this takes into account frequency of collisions. So this is generally constant across all temperatures. And something specific about it is not just the frequency of collisions, it's the frequency of collisions, but with proper orientation. If we refer back to collision theory, we need the correct orientation. So this is how we determine, this is one part of K. This is the part of K that considers how these molecules are interacting and how they are reacting with each other and whether or not they are in the proper orientation to do so. So that is what our Arrhenius factor specifically indicates. Once again, it has the same units of K, and it does actually vary a little bit with temperature, but it's generally negligible. So we consider constant across all temperature values. All right, so that is our Arrhenius factor A. If we rearrange our Arrhenius equation, we can actually isolate A and say A is equal to the rate constant K divided by Euler's number raised to the power of the negative activation energy divided by RT. So we can solve for A just by rearranging our equation given the other values. Now, the next part is, what is the other half of this K? So what is therefore our E to the negative EA over RT? So if A accounts for the collision with proper orientation, this section that starts with Euler's number, this actually refers to fraction of particles with energy greater than or equal to our activation energy. So now that we understand these two parts, we can look back at our equation and see that the rate constant K is a function of the fraction of particles that have the correct orientation and the fraction of particles that have the correct energy to react. And so that is all what goes into determining our rate constant K, which is proportional to our rate. So this is what this whole equation describes. Now, really quickly, before we move away from E to the negative EA over RT, we can see from the equation that this is dependent on rate, or sorry, dependent on temperature. And furthermore, it is also dependent on our activation energy. So it's dependent on temperature and the energy required to react. So now that we have an equation, we can do something quite wonderful. We can rearrange the Arrhenius equation to figure out any variable value given other values. So this can help us solve for pretty much everything in our equation. So as we explore this, we know that R and T, or sorry, not R and T, R and E are constants, so we don't need to figure those out. K and P can be determined experimentally. So we don't need to figure those out either. So the real part this equation helps us is figuring out our Arrhenius factor and our activation energy. So those will be measured indirectly. Now, because we have two variables that we need to figure out, but we only have one Arrhenius equation, what we actually do is we figured out by graphing data. So we graphed data, and by graphing this data, we can create a linear expression to figure these out. It sounds weird because we have such an odd equation, but we're actually going to be able to turn our Arrhenius equation into a linear expression that we can then use to measure what the individual variables of our Arrhenius factor and activation energy are. So we will start with our Arrhenius equation, and I'll swap colors for this part. So K is equal to our Arrhenius factor times Euler's number raised to the negative activation energy divided by RT. Now, because we have Euler's number, we can usually assume the first thing that we're going to do is take the natural logarithm of both sides, which we do. So ln of K is equal to ln of A e to the negative E A over RT. Now, when we have two variables multiplied together, we can actually separate those out. And because we're separating them out, and one of them is already Euler's number, which is the base of the natural logarithm, we can then rearrange that further. So we can convert this into ln k is equal to negative EA over RT plus the natural log of our Arrhenius factor. So we can then take this one step further and pull the inverse of t out of this, creating ln k is equal to negative EA over R times 1 over the inverse of, 1 over t plus ln of A. Now, if we look at this very carefully and We play a little pretend. ln of k is y, negative EA over R is M, 1 over T is X, and ln of A is B. This is the equation for a line, y equals mx plus b. I'm going to switch that to a lowercase b. So what this means is that we can graph this as a linear plot. If we specifically graph the ln of k on the y-axis against 1 over t on the x-axis, we will get a line. We get a line. This is known as the Arrhenius plot. So when we do that, we can explore this graph right here. This is ln of k. This is 1 over t. And we will get a line with a negative slope. We can see from the slope that the gradient, the slope or gradient, is equal to negative EA divided by R. So this is a representation of our activation energy. If we extrapolate our line a little bit to get our y-intercept, that y-intercept is now just ln of A. And this is what we can figure out by taking the natural log of k and setting it equal to our equation. This is our Arrhenius plot. We can figure these out super easily because R is a constant, so we can just take the slope, or sorry, we can just set EA equal to negative slope times R, and that's our activation energy. And then to get A, we just have to rearrange our logarithm the same way we do for pH and concentration. We also, furthermore, could just find A from the previous rearrangement of the Arrhenius equation. Anyways, this is the graphical representation, the Arrhenius plot, and how we solve. You can solve for any problem just by taking data points, graphing them, and then connecting the graph with a line, solving for the slope. Sometimes you do not have enough data to make a graph. You only have 2 points, and so this is the other way we can do it. We can calculate our activation energy without a full plot. We just need 2 points. This is similar to point slope form, if you remember that from math classes. Point slope form. So whenever we have 2 points, like whenever we have 2 points, like 2 rate constants, we can take both of those and put them into our equation, and we get this version of our Arrhenius equation, 1 over T2 minus 1 over T1. So now we can solve for the activation energy by only using 2 temperature and 2 rate constant datas. We'll do a quick example of this before we finish off today's video. So in this example, through experimental data, we found that K1 is equal to 7.78 times 10 to the minus 7th. We're not going to really worry about units. And K2 is equal to 3.46 times 10 to the minus 5th. Our temperature for our first equation was at 273 Kelvin, and our temperature for our second experiment was at 298 Kelvin. All we have to do is plug these values into our formula, and we find that the natural log of 7.78 times 10 to the minus 7th divided by 3.46 times 10 to the minus 5th is equivalent to EA over R times 1 over 298 minus 1 over 273. Once we plug both of these values in our calculator, we will then get negative 3.79 is equal to EA over R times negative 3.07. What I will then do is bring those both to the other side and get our activation energy is equal to negative 3.97 times our gas constant, 8.31, all divided by negative 3.07. Sorry, I made a mistake here. It's 3.07 times 10 to the minus 4th. And 10 to the minus 4th. And solving for our activation energy, we find 1.02 times 10 to the 5th, and we know our units are going to be joules mole inverse. So this is it for the Arrhenius equation. This is kind of what we use it for. We can calculate our activation energy from any 2 points using an adaptation of the Arrhenius equation, or we can calculate our activation energy as well as our Arrhenius factor via the graphical representation of it. Remember, if you're finding the graphical representation, ln A is going to be equal to our y-intercept, which just is if we plug 0 in for 1 over temperature, meaning that ln of A will be equal to the ln of K at that point. All right, so that is it for our equation. That is it for the Arrhenius factor. I hope this helps and have a great day.